All right. I got a problem from one student yesterday, and thought I'd work it out. Show you how these problems with heat work out. And this is, what you can expect on an exam or quiz. It's not just a straightforward heat problem. It is something that requires some thought, and so the first thing you need to do is let's the I'm going to write down the particulars of the problem. And what you have is you've got a 28 gram metal slug, 28.0 gram metal slug. We'll just say M for slug, all right? And the initial temperature of this metal slug is 99 degrees. So they've heated it up, okay? And so then this is constant pressure calorimetry, so that means it's like a coffee cup. So here's my coffee cup, and inside this coffee cup initially is 65 grams of water. So we know what the water temperature, we know how much water we have, 65.0 grams of water. And I assume this is 99.0. I don't didn't write it down that way, but to keep three significant figures, that's what it needs to be. All right, and the initial temperature of this water, let's make it TWI, equals 24.0 degrees Celsius. All right, so then you place the metal slug into the water. So here's my metal slug into the water. And what happens is, because the metal slug is hotter than the water, the heat will flow from the metal slug to the water. And then it also flows to the calorimeter. So you got to keep that in mind too. It's actually going to flow into the calorimeter there. All right. And we see that the final temperature of the whole system is equal to 28.4 degrees Celsius. All right. And the question is, they'd like to know what the specific heat of this metal is. And they tell us that the heat capacity of the calorimeter is equal to 13.4 joules per gram degree Celsius. Or joules per degree Celsius. Yeah, all right. So how do we solve the problem? Well, the heat equation for this is Q equals specific heat times the mass times the change in temperature. So we know what the mass is. We can determine the change in temperature if the change in temperature would be 28.4 degrees Celsius minus the initial temperature of 99.0 degrees Celsius. So let's calculate that out. Equals negative 70.6. All right. Degrees Celsius. We know what the mass is. We're going to plug that in there. So what we don't know is the heat. All right. Now, if we had the heat, we could solve for the specific heat, which is what the question's asking for. So how are we going to find the heat? Well, the Q of the metal is equal to the Q of the water plus the Q of the calorimeter. And all of that's negative, right? So let's talk about this. I think this is where most students they're not quite getting the concept here. So let me just remember this, that energy is not created or destroyed in the universe, that delta E of the universe, or if you look at our book, it said delta U of the universe is equal to 0. So whatever heat is lost by the metal must be gained by the water and the calorimeter. So in order to solve this problem, we have to determine the Q of the water and the Q of the calorimeter. Now you go, well, can that be done? Well, let's look at it. Let's look at the Q of the water. The Q of the water, you know that the specific heat of water is 4.184 joules per gram degree Celsius. You know the mass of the water, which is 65.0 grams. And you know the temperature change of the water, which is the final temperature is 28.4 degrees Celsius minus the initial temperature of 24.0 degrees Celsius. So if we multiply that all out, we'll get the Q of the water. So let's do that. And this should be endothermic, right? The heat leaves the metal slug and goes to the water and causes the temperature of the water to rise. So 4.184 times 65 times 28.4 minus 24.0. Okay, so that gives us 1,196 joules of heat absorbed by the water. All right, so that gets this part. Now, we got to solve for the Q of the calorimeter. Well, that one's not too bad either. Q of the calorimeter is equal to the heat capacity of the calorimeter times the temperature change of the calorimeter. Well, the calorimeter and the water would be the same temperature, so, and the final temperature would be the same. Otherwise, heat would keep flowing. So 28.4 is the final temperature minus the initial temperature of 24.0. So if I calculate this out, I'll get the Q, the heat absorbed by the calorimeter. And again, it should be a positive value because the heat's going from the slug to the water to the calorimeter. So 13.4 multiplied by 28.4 minus 24. And that gives us 58.96 joules. Okay, so what we have now is the Q of the metal is equal to negative 1196 joules due to the water plus 58.96 joules due to the calorimeter. So we hit those together, we get equals plus 1196, 1254.96, 1254. I'm just going to say 1255 at this point. Only had three significant figures. All right, and we're going to round off at the end anyways. All right, so we got 1255 joules. And that quantity is negative because that is now the Q of the metal. That's how much heat the metal gave off. Negative 1,255. All right, so now we're going to put in a negative 1,255 joules in for here. And now we're going to, and then we're going to, so we're going to solve for specific heat. So we're going to divide this Q by the mass of the metal, which is 28.0 grams. And then multiply that by the temperature change, which is 28.4 minus 99.0 degrees Celsius. All right, and again, the negatives will cancel out here, so this is going to work out perfectly. So we got a negative 1255, or I got, okay, 1254.96. But we'll round it off at the end. All right, divide that by 28, and divide that by parentheses 28.4 minus 99. And we get 0.634 or 0.635. So we get an answer of 0.635 joules per gram degree Celsius. So there's our answer right there. That's the specific heat of the metal slug. All right. So let me just say again what you're doing on all these problems. You're collecting the information that's in the problem here and here and here, And then you know the metal slug is at a higher temperature than the water initially. And so the heat is going to flow from the metal to the water, and then from the water to the calorimeter. And so the Q of the metal is negative the Q of the water plus the Q of the calorimeter. So then it's just a matter of solving for, again, for this to be solvable, you have to find out what the Q of the metal is. All right. And how do you find the Q of the metal? You got to find the Q of the water and the Q of the calorimeter. Once you get the Q of the metal, then it's solving for specific heat in the heat equation for the metal. And that's how you solve for the Q of the water. How do you know to use the Q of the water? Well, specific heat of water, you should have memorized the mass of the water, temperature change. There's the heat equation to determine how much heat's absorbed by the water. Now, they gave you the heat capacity of the calorimeter, so you should say Q equals cat, which is the heat capacity times the temperature change of the calorimeter, which would be the same as water. So we find out the joules absorbed by the calorimeter, and now we have these two items or terms, and we can add those together and find out what the Q of the metal is. And it's opposite, so it is a negative value because Q of the metal, it is a release, so it's an exothermic process. So I hope that helps. I know these aren't the simplest problems, but they're not difficult in that it is simple math. It is a matter of, the whole thing really is the thought process. And I understand that the guided solution may be confusing because they combine all this into one big equation. And people don't normally solve things that way. They usually want to break it down into components and then put the components together. So I understand that the guided solution, and they did that to compact the solution. So I understand that. So I hope this video helps. And again, it's a system of equations. You're going to see that in Chapter 5. If you've seen it in the homework, you've seen it on the quiz, you're going to see it on the exam. It's not just straightforward heat equation. Yeah, that's what I would do if I was teaching introduction physics and chemistry. But we're doing a little bit more like real world type problem what you do in the lab, where you heat up a metal slug, drop it into a known quantity of water that has that you've measured the initial temperature, and then from that you can determine something like the specific heat of a metal.